I'm Carl Haber, a scientist in the physics division at Lawrence Berkeley National Laboratory. Together with my colleague Vitaly Fadeev, we invented the Berkeley Optical Sound Restoration System to address two problems related to our cultural and historical legacy. The first is to preserve rare, delicate, or damaged recordings on mechanical sound carriers, which are considered too fragile and too valuable to be recovered by standard commercial methods. The other is to provide access to the general public and to scholars to the large collections of sound recordings which reside in archives and libraries.
I'm Vitaly Fadeev. Let's have a look at some of the old mechanical audio carriers from which our system can restore the sound. The history of recorded sound started in 1877 by sound being embossed on foil. Groove is here modulated vertically. It goes up and down on the surface of the foil. Then the technology went on to adapt the wax cylinders and then plastic cylinders. And then at around late 19th century, the technology went on to adapt the shellac discs. The instantaneous recordings were made on acetates. There are some problems of them, such as flaking out of the lacquer area from the surface. Instantaneous recordings were done on specialized media. Here's one piece used in World War II era. And then in 40s and 50s, dictabelts were used for monitoring and instantaneous recordings of voice content. In principle, our system can be used to scan even broken record piece by piece and then try to reassemble the sound each to one.
Let's look at how the Berkeley Optical Sound Restoration System actually works on media such as a cylinder, where the sound is encoded in an up and down movement of the surface. The central idea of the method is to create a non-contact map which is in digital form, and that map can then be analyzed by a computer with no risk from touching the medium. What we use is an optical scanning device called a Confocal Probe. This probe accurately measures the distance to a small region of the surface, a few microns in diameter. Coupled to precision motorized stages under the control of a computer, we can scan the probe along the surface and rotate the cylinder in order to cover the entire surface area with confocal measurements. We then achieve a map of the entire surface, which can then be analyzed to both remove debris and damage and also extract the sound. What's shown on this screen is the result of the scan taken with the Confocal Probe on a wax cylinder. Each of these lines corresponds to one sweep of the probe along the axis of the cylinder. The sound is stored in a groove which spirals around. Each line is at a different angular position around the circumference of the cylinder. The sound is encoded in the depth of the groove, so each of these regions would move up and down as the sound changes. In certain places, we can see that the shape of the surface is very much not like the groove, and those are easily identified by our algorithms as sites of dust, damage, or debris. Because they don't match the expected groove profile, we can recognize them and remove them from the data, thereby improving the sound and restoring the recording. Following this, each scan is combined into a full surface map, which is shown in this plot. This axis shows position along the axis of the cylinder. This is the height measurement from the probe to the surface. And this is position around the cylinder. So this data should be viewed as coming back on itself. The fact that this shows a non-uniform structure, that it's tilted, is indicative of the fact that the cylinder is not really a perfect cylinder, but is in fact deformed, off-center, and perhaps tapered. But because the Berkeley Optical Sound Restoration System captures a full map of the surface of the medium, we can correct for these deformations, which if not corrected for, would lead to low-frequency noise. as part of the analysis. In the years when cylinders were in use as a recording medium, they would have been played and recorded on a device that looked something like this. The cylinder would rotate on a spindle, a stylus would be in contact with the surface, and it would be excited by or excite a diaphragm, which would then couple the sound to a horn. When collectors or libraries or archives listen to cylinders now, they use a device which is similar to this, but is a modern form. When we listen to the cylinder of Just Before the Battle Mother, played with a stylus, it's actually played on a modern version of this with an electrical pickup. Now let's listen to the same cylinder scanned using the three-dimensional confocal scanning technique, analyzed and processed to extract the sound. Here we've taken the optically scanned cylinder recording of Just Before the Battle Mother and added a chosen equalization and additional filtering to it. Let's see the way the system works on a monaural disc recording. Here, the groove undulates from side to side. Therefore, it's not necessary in all cases to use the 3D method. In many cases, we can use a high-resolution imaging system based on a digital camera and appropriate optics. Here's a CCD camera, here's a microscopic lens, and the light is focused down onto the surface of this disc. The disc sits on a turntable which rotates and translates under the control of a computer, which also acquires images from the camera. Here on the monitor, we see at low magnification an image of the groove. The fine white line down the center is the bottom of the groove. The black area is the sloping walls of the groove. You can see small scratches and debris from place to place, and you can see also the undulation, which is the sound information stored in the groove. If we bring the magnification up and get a high resolution image, what we see is this. And when we actually acquire images, we work at these higher magnifications. We acquire thousands of these images, which can then be analyzed by the computer to extract geometrical information which characterizes the sound stored in the groove, and then analyzed and processed to remove the effects of debris and damage if needed, and finally the stylus motion can be modeled and the sound extracted. As we've shown, the Berkeley optical scanning process uses both a three-dimensional approach and a two-dimensional approach. The 3D approach speaks most directly to the needs of preservation, where we want high resolution, very complete measurements of the surface of the media. The 2D approach gives us less information, but is in principle a much faster way of scanning a disk. For the purpose of access, the Library of Congress has asked the laboratory to design a workstation where the 2D process would be implemented, and this would be evaluated by them as a method of massively digitizing discs, acetates, lacquers, cellulose, which reside in their collection. And through that process of mass digitization, greater access could be granted to scholars and to the general public into this collection.